Hello, abstract algebra students. In this screencast, we will prove that the symmetric difference is well defined on the power set. We have already proven that the symmetric difference is commutative and associative. Well defined, however, is a longer proof that requires more than a truth table. Because this proof is so long, it is not really going to work for me to type it in real time. So I have already typed it into a PowerPoint, and I will animate the PowerPoint and discuss it. Feel free to pause the video as you need to if you need more time to digest what is being said. So our claim is that symmetric difference is well defined on the power set. We want to show for all a, b, y, z in P of m, if both a equals y and b equals z, then a triangle b equals y triangle z. So our elements a, b, y, z are sets here, so we use capital letters. Our set is the power set, or the set of subsets of m, and our operation is the symmetric difference. Otherwise, this is just the normal definition of well-defined. So to begin the proof, we have a quantified if-then statement. So we let a, b, y, z, and p of m be given. We'll assume the if part that both a equals y and b equals z. And now we'll consider the following claim. Notice that because this is an if-then statement rather than a set theoretic identity, we need to element chase to prove it. So our element chasing here is we apply the definition of set equality to the then part that we want to prove. So we want to prove for every element x is in asymmetric difference b, if and only if x is in y symmetric difference z. So to begin with this proof, we'll let x be given, but because this is an if and only if statement that we're trying to prove, we need to prove it forwards and backwards. So our forwards claim is going to be if x is a member of A intersection B, then x is a member of Y intersection Z. And our backwards claim is going to be if x is a member of Y intersection Z, then x is a member of A intersection B. Once we prove the forwards and backwards claims, we'll wrap up the forwards and backwards by saying, therefore, having proven both directions, we may conclude that x is in asymmetric difference B if and only if x is in y symmetric difference Z. And we end our element chasing by saying, therefore, having proven for all x is in asymmetric difference B if and only if x is in y symmetric difference Z, by definition of set equality, we may conclude that asymmetric difference B is y symmetric difference Z. Okay, this is the overview of the proof. However, we still have to do the work. We still have to do the element chasing. We have to chase x from asymmetric difference B to y symmetric difference Z. And then we have to chase x from y symmetric difference Z to asymmetric difference B. So to do our forwards claim, if x is in asymmetric difference B, then x is in y symmetric difference Z. We'll assume the if part, assume that x is in asymmetric difference B. Since we know that x is in asymmetric difference B, by definition of symmetric difference, it follows that either both x is in A and x is not in B, or both x is not in A and x is in B. So now we need to split into cases. Assume that both x is in A and not in B. Well, since we know that x is in A and A equals y, definition of set equality gets us x is in y. Since we know that x is not in B, but B equals Z, B and Z have to have the same elements. So by definition of set equality, x is not in Z. However, now that we know both x is in y and not z, that means x is in one but not the other of those two sets. So by definition of symmetric difference, we may conclude that x is in y symmetric difference z. That was our first case. Now in our second case, we make a similar argument, but starting with the assumption that x is not in A, but x is in B. So assume both x is not in A and x is in B. Since we know that both x is not in A and A equals y, definition of set equality gives us x is not in y. Similarly, since we know that x is in B and B equals z, by definition of set equality, it follows that x is in z. Therefore, since we know that both x is not in y and x is in z, by the definition of symmetric difference, we may conclude that x is in y symmetric difference z. Now, notice that in both cases, we ended up with x is in y symmetric difference z. So, therefore, having proven x is in y symmetric difference z in all cases, we may conclude that x is in y symmetric difference z. And that is our forwards claim. We assumed that x is in asymmetric difference b and argued that x is in y symmetric difference z. Now, backwards claim works very similarly, but we start out with x is in y symmetric difference z. Assume that x is in y symmetric difference z. Since we know that x is in y symmetric difference z, by definition of symmetric difference, it follows that either both x is in y and x is not in z, or both x is not in y and x is in z. Consider the following cases. So in the first case, we assume that x is in y but not z. Since we know that x is in y and a equals y, definition of set equality gets us to x is in a. Since we know that x is not in z but b equals z, definition of set equality gets us to x is not in b. Therefore, since we know x is in a and not b, it's in one but not the other of those two sets. So by the definition of the symmetric difference, it is in the symmetric difference. And similarly with the second case, we start out both x is not in y and x is in z. Since we know that x is not in y and a equals y, by definition of set equality, we get x is not in a. Now, since we know that x is in z and b equals z, definition of set equality gives us x is in b. So now that we know that x is not in a, but it is in b, by the definition of symmetric difference, we can conclude that x is in asymmetric difference b. End the cases by saying, therefore, having proven x is in asymmetric difference b in all cases, we may conclude that x is a member of asymmetric difference b. And we've done the backwards claim. Assuming x is a member of y intersection z, and proving that x is a member of a intersection b. So this is the overall structure of the proof. However, there's a bit of an adventure in proving both the forwards and the backwards claim of our element chase. We end up assuming a equals y and b equals z, and end up proving that asymmetric difference b equals y symmetric difference z, given that symmetric difference is well defined. Okay, we will do closed next.